Hello everyone, in this video I will discuss previous year's questions acidity-basicity related of CSIR-NET. So let's start. The first question we have to find the pK values of the following compound. Different orders are given in the options. So here we have 3 compounds and the common point is all of these are 1,3-dicarbonyl compounds. Right? Now in this 1,3-dicarbonyl compounds, if we consider this middle methylene group and if we remove this hydrogen, there will be a negative charge. So we will try to see in which case this negative charge is maximum stable. Now in A and B, the negative charge is stabilized by these 2 carbonyl. But remember here in case of B, because of this OMe group, there will be some competitive resonance. That means the full electron withdrawing effect from these 2 carbonyl group in 1 and 3 position, we will not get in case of B. So A will be more acidic than B because in case of A, the negative charge is more stable. The double bond character of C double bond O, it is less in case of B. So that is why its electron withdrawing effect is less. So negative charge is less stable in B compared to A. So A is more acidic than B. Now what about C? C is basically ester, but it is cyclic ester. In case of cyclic ester, one more extra information we need to answer this question. Now ester I can write in 2 ways. So here the lone pair is here and R prime and CO, they are on the same side. These two are on the same side, so that is why I am writing here C's. But the other possible orientation, now the lone pair is this side and R prime. Now R prime and CO, these two are trans to each other, right? Now why I am doing this? Because when there are C's and trans, there is some extra stabilization possible, but that is only in case of C's. Now this information you can get, here page number I have already mentioned. So see, when it is C's, it is basically just imagine as if it is cyclic. So in case of cyclic, this C's is actually not possible because it is locked. Here see, this carbonyl and this is basically our R prime. This part is R prime. So R prime and C double bond O, they are in trans, and that will always be the case in case of cyclic ester because it is locked. So this trans orientation we will get in case of lactone. Now what is happening here? In this conformation, that is C's, additional stabilization is possible as second lone pair of oxygen donates into CO sigma star. So here the first lone pair, which is the green one, that is donating electron to the pi star, that is the orange orbital. But if we consider the another orange, means this orange orbital, which is that is a normal delocalization that we know happens in case of ester. But this second lone pair, that can donate electron to this black one, which is sigma star. But this type of effect is not possible in case of trans. That is, this additional stabilization is not possible. So second lone pair of oxygen cannot donate it into the CO sigma star. So that is why in case of trans, the C double bond O, it can show more electron withdrawing effect. And that is the reason C will be more acidic. This effect is so high that it can even overcome A. So C will be even more acidic than A. And this compound is basically known as Meldrum's acid. So the name itself, there is the term acid present. So if this is the order of acidity, the pK order, that will be reverse. Acidity is CAB and it will be BAC because pK and acidity, these two are inversely related to each other. Next question, correct order of pK. So first we will see the acidity so that we can understand pK. Now to understand acidity, here we will remove this hydrogen, and if hydrogen is removed from this position, there will be negative charge. Now for this negative charge, this compound now it will become anti-aromatic, right? After the generation of negative charge, this will become aromatic. And here, after the removal of hydrogen, negative charge, if we consider total 8 pi electrons, at a first glance it seems it is anti-aromatic, but as it is a large structure, planarity will not be maintained, so ultimately it will be non-aromatic. But even if you have confusion between A and C, one thing we are sure that B will be more stable after this negative charge generation because it is aromatic. That means it will be maximum acidic, and maximum acidic means minimum pK. So B should be at the minimum position. That means this option should be right. So if we are sure about it, then also we can choose the correct option. So this is the correct option. And why A is greater than C? That is why C is more acidic than A. It is because it is non-aromatic, and non-aromatic species, they are comparatively more stable than anti. Anti is maximum unstable, then non, then aromatic. Okay, so this is the correct answer. Correct order of basicity of the following anions. Now if we want to understand basicity, first we will see what is the stability order for these anions. So if we know which species is maximum stable, actually that species will be minimum basic. Because high basicity means what? It is very reactive. It is searching for a H plus. And if it is stable, obviously it is not searching for H plus, right? So stability order, if we know, the reverse will be the basicity. So here maximum stability, that will be for C, because here we have total 3 NO2, not just plus I effect, minus I effect, but it can also show minus M effect. So C will be maximum stable. After that it will be D, because in case of D, even if you are simply focusing on this part, here because of resonance, 2 equivalent resonance structures we can get, and that is the reason it is very stable. After D, the next species will be among these two, with these two are not aromatic. Next will be A, because in A we have NO2, which is more electron withdrawing than CSIR. So if this is the order C, D, A, B, the reverse will be the order of pK, that is B, A, D and C, that you can find in option 4. The correct order of basicity for the following heterocycles. Now in these 3 heterocycles, in case of A, we have one nitrogen, the other 2 we have 2 different nitrogen. So let's first look at A. In case of A, this lone pair, it will be undergoing this type of delocalization, and once it is occurring, it will be very stable, because now it is having some aromatic character. Now this lone pair availability over nitrogen, because of this reason, is very low. That means this will be minimum basic. So if A is minimum basic and we have to find correct order of basicity, that means A should be at the last position. So 3 should be the correct option. This much information is enough to choose the correct option. But why C is more basic than B? If we want to understand, then this will be the explanation. Now here we have 2 different types of nitrogen. I am numbering it 1 and 2. So what is the difference between 1 and 2? 1 is NH and 2 is double bonded nitrogen. Remember, always when you have this type of 2 nitrogen, the number 2 nitrogen is the nitrogen which will be protonated. So that is why C, from B after protonation you will get this structure, from C after protonation you will get this structure. So 1 nitrogen is not protonated, only the double bonded nitrogen protonated. Why? Because if you protonate number 1 nitrogen, it will be NH2. In that case, delocalization not possible. So only the nitrogen which is part of C and double bond, that nitrogen will be protonated. Now in this case, which we are getting from B, there is no inductive effect we can get from these 2 sides. Okay. But in case of, because there is no nitrogen, sorry, not this side, I am talking about this side, it is possible because here we have carbon. But the other side we have nitrogen. I am talking about N2. Just focus on nitrogen 2. Here inductive effect is coming only from one side, but in the second case it is coming from both sides, because nitrogen is far from this at 3 position. So that is why it will be having some more stable character than the B. So from C, as we are getting, that is after protonation, we are getting stable conjugate acid, because we are talking about basicity. So if the conjugate acid is very stable, that means basicity is high. You can also write it like this. Suppose this is base and you are protonating it, you are getting BH plus. So these two are basically BH plus. B means base. So when BH plus is very stable, obviously means B is very basic. So that is why C is more basic than B. This is the correct option. The order of pK values we have to find. We have 3 different species. All of these are in protonated state. Now step by step we will try to solve this problem. First of all, what I will do, all these protonated species, if I write it in this way, I pair to NH2 means 2 isopropyl groups attached to NH2. Now if these that is protonated species, suppose I am writing it as HA plus. So this is HA plus, this is another HA plus, this is another HA plus. Total 3 type of HA plus. So if you remove this H, the corresponding species, I am writing it as A. So these 3 are A. Now consider this equation, that is HA plus. If you are removing H plus, you will get species A. So in this equation, the equilibrium will be shifted towards right hand side. If A is becoming more stable, that means if A is weaker, more stable means what? Weak, not very reactive. And when A is more stable, that means it is less basic, because more basic means what? It is highly reactive. But we are saying more stable, that means it is less basic. So you can explain it in 3 different ways. You can say more stable is A, you can say weaker is A, or you can say less basic is A. All these are same thing. So when it is happening, that means higher is the acidity of HA plus. The tendency of this, that is, it will be shifting towards right hand side. So more H plus we can get. More H plus we can get means lesser is its pKa. So here this is the relationship. If it is so, now the acidity and basicity order of A and HA plus will be like this. So basicity order of A. This is our A, 3 different A. Now why it is maximum basic? Because here the lone pair availability over nitrogen, that there is two inductive effect from these two groups. But in case of pH and H2, this lone pair over nitrogen, that will be involved in delocalization with the pH. And in the third case, there are 2 pH. That means more the chance that there will be no, that is a lone pair availability over nitrogen will be very low. That is why this is a basicity order. Now if it is a basicity order, acidity order will be reverse, as we have seen this explanation here. So if this is the acidity order, that means pKa order will be reverse. Maximum pKa will be for this one, max. This is mean, and that you can find in this option, that is second one. Okay, so in this way, step by step, applying this logic, we can understand the correct order of pKa values. Again, correct order of pKa values for compounds XYZ. Now obviously I will consider the middle one first, because see here, if you remove this hydrogen, there will be negative charge. So because of this negative charge, now the species is aromatic, and not just aromatic, because of this 5CN group, this is highly stable because of electron withdrawing group. So it is aromatic, it is getting some electron withdrawing effect. So because of all these reasons, this negative charge is very stable. That means Y should be maximum acidic. So if I am considering the acidity order, then Y should be maximum acidic. Now after Y, if we remove hydrogen and we are getting a negative charge here, now you can say this is also aromatic. But see, if you are considering delocalization, then what will happen? The aromatic character of this right hand side ring, now that will be lost. Fine. So though we are getting aromatic species because of this negative charge, but there is another factor which is hindering the stability, right? Now what about X? In case of X, when there is negative charge after removal of this H, it is stabilized in both sides, right? So that is the reason it is more stable than Z. So Y is maximum acidic, after that it is X, and then it is Z. Now if it is the case, reverse will be the pKa order. So acidity order Y first, after that X, which is basically thalamide, and then we have at last Z. YXZ, that means ZXY will be the pKa order. Correct statement about the reaction of X and Y. We have two species given, X and Y. It is reacting with NaNH2. NaNH2 is nothing but base. NH2 minus amide ion, it will capture this H. Now when this H is removed, there is negative charge here. So the negative charge that we are getting from X, it is basically pH3C negative. And in the next case, we are getting a species which is anti-aromatic like this. Whatever is the substituent, after all, this species is anti-aromatic because of 4 pi electron, right? So that is the reason this species is not stable. So after reaction with NaNH2, the species we are getting not stable from Y. That means X should react fast compared to Y. So A should be correct. Now among A and B, because these two are same type of option, so any one of these will be correct. Now among C and D, which one is correct? C is saying these two are Lewis acid, but Lewis acid means it will accept lone pair, but it is not accepting lone pair. It is matching with the definition of Bronsted acid. That means where H plus is donated, that is actually the Bronsted acid. So in this both cases, basically NH2 is capturing H, so it will be not Lewis acid, it is Bronsted acid. So among A and B, A is correct. Among C and D, D is correct. So A and D will be the correct options. Correct order of basicity. So again see, if you know the stability order, you can understand the basicity order. So first we will try to see which one is more stable. So stability order, if we consider, then 2 will be maximum stable, because in case of 2, this NO2 can show only the negative inductive effect, not resonance possible, because it is in meta position. Now in case of 1 and 2, in both cases, both inductive effect as well as minus M effect is possible. So 2 will be maximum basic. Now if 2 is maximum basic, that we can get in two options, right? A, C. So still we have to discuss among 1 and 3 how to know which one will be more basic. Now if you add a H plus here, the conjugate acid that you get, it will be OH, and if you write NO in extended way, there is hydrogen bonding possible like this. So after capturing H plus, it is becoming more stable. This type of intramolecular hydrogen bonding you cannot get in case of 3, right? So this species is becoming more stable after capturing H plus. That means this should be showing more basicity than 3. So considering all this, after 2 we have already decided it is at first position, which you can get in A and C, but after 2, among 1 and 3, it will be 1, which is more basic. So that is why it is correct option. This is very interesting. The increasing order of pK value of marked hydrogen. That means this hydrogen it is talking about. Circled. Now here, first we will try to see which one is maximum acidic. If you remove H and if you write the negative charge, then from the middle species, what we are getting? If you write it here, though the positive charge it is delocalized over this N, C and N, but if I write it like this, NH2, NH2. Now see this negative charge, it is not just stable by resonance towards cyanoside because of this type of resonance possible, but the resonance is also possible this side. So this species is very much stable because of this type of delocalization. So 2 should be maximum acidic. If 2 is maximum acidic, its pKa should be minimum. That you can get only in option B. So this much information, from this information we can choose correct option. But among 1 and 3, if we want to compare, the negative charge in first compound, resonance is possible both sides. But see, in case of compound 3, after generation of negative charge, this negative charge is basically localized. Delocalization is not possible. So that is why it is not getting any stability. So 1 should be more stable. That means the pKa, it should be sorry, no, I'm not talking about stability. Stability is in terms of negative charge. But if we consider which one is more acidic, 1 will be more acidic. So here if we consider these points, negative charge in conjugate base of 2 is highly stable. This one. Then negative charge is localized in the conjugate base of 3. Unlike conjugate base of 1. In case of conjugate base of 1, negative charge is not localized. It is localized only in case of 3. So acidity order will be, maximum is obviously 2, but after that it is 1 and then 3. So the pK order, that should be reverse. 3, then 1 and then it should be 2. So it is matching with C. Fine. Decreasing order of basicity of the following compounds. So in all these compounds, only in the last one we have single nitrogen. This is basically pyridine. So in this case, once you protonate it, that is the conjugate acid if we consider, this is not getting any stability because here delocalization is not possible. That is, positive charge is localized. Delocalization is possible within this ring. These three double bonds, they can change their position, but the positive charge is not localized, right? So that means this is not very stable after protonation. So this is minimum basic. Now if this is minimum basic, 4 is at last position that we should get, right? But what about the other one? The other three, there is 3 more compounds. The other 3, we have nitrogen, 2 nitrogen in case of 1 and 2, 3 nitrogen in case of compound 3. Now this structure you can have some, it is analog of guanidine. See, which is having this type of structure. I am talking about guanidine. It is also just like that. So here only this nitrogen, which is part of double bond, that will be protonated, because only when it is protonated, I am just protonating it, then resonance from both sides is possible, and that is the reason it is very basic. Among all these, this will be the maximum basic. Now if 3 is maximum basic and if 4 is minimum, that means option 3, that should be the correct option. But in option 3, 2 is before 1. So why 2 is more basic? Let's try to understand. So in case of 1 and 2, I am just numbering it. This nitrogen will be basically protonated, which is part of the double bond. And here this nitrogen, which is part of the double bond, that will be protonated. So resonance is possible like this. Here also it is possible. But what is the difference between these two? In case of 1, after protonation of this nitrogen, that is H, both sides there is carbon, right? But in case of this one, that is a second compound, one side we have carbon, another side also we have carbon, but these two carbon we have some difference. In the first compound, both these carbon are sp2 hybridized, but in the second compound, this carbon is sp2 but other carbon is sp3. So one carbon is sp3, that means electron withdrawing tendency is not so high. So which one is getting more stability? Obviously 2, because here one carbon is less electron withdrawing in nature because of its sp3 hybridization character. So that is the reason after 3, max and mean we know, but after 3, 2 will be coming before 1. So this is the correct option. The correct order of acidity of the compound ABC. The last compound, this is called squaric acid, and this is, the name itself is saying it is acid, and its acidity is very high, and it is basically diprotic acid. 2 hydrogen you can remove. Now if I remove only 1 hydrogen, then also you will see here extended conjugation is possible. So this negative charge, it can be stabilized like this. So it is extended over this whole region, right? But if I consider A and B, here negative charge, that is stabilization is possible by delocalization both sides, here also, but it is not like C. So C will be maximum acidic, and if C is maximum acidic, it is squaric acid, then obviously option C should be correct. But why A is more acidic than B? Now in case of B, we also have a benzene ring, and because of this benzene ring, this type of delocalization is possible. That means the double bond character of these 2 carbonyl carbon, which it will be having less electron withdrawing, less stabilization for this negative charge, because its double bond character is decreased because of this delocalization with the benzene ring. But that is not possible here. Here full electron withdrawing effect from these 2 carbonyl group possible. So that is why A will be more acidic compared to B. So option C, that is the correct option. So that's all I have in this video for you. If you find it helpful, please like, share and subscribe. I will meet you in the next video. Thank you for your time.